The covariant formulation of classical electromagnetism refers to ways of writing the laws of classical electromagnetism in a form that is manifestly invariant under Lorentz transformations. In the formalism of special relativity using rectilinear inertial coordinate systems, these expressions both make it simple to prove that the laws of classical electromagnetism take the same form in any inertial coordinate system, and also provide a way to translate the fields and forces from one frame to another. However, this is not as general as Maxwell's equations in curved spacetime or non-rectilinear coordinate systems. This article uses the classical treatment of tensors and Einstein's summation convention throughout, and the Minkowski metric has the form diag, where the equations are specified as holding in a vacuum. One could instead regard them as the formulation of Maxwell's equations in terms of total charge and current. For a more general overview of the relationships between classical electromagnetism and special relativity, including various conceptual implications of this picture, see classical electromagnetism and special relativity. Covariant objects. Preliminary 4 vectors Lorentz tensors of the following kinds may be used in this article to describe bodies or particles. 4 displacement. 4 velocity, where gamma is the Lorentz factor at the 3 velocity u. 4 momentum, where p is 3 momentum, e is the kinetic energy, and m is rest mass. 4 gradient. The D'Alembert operator is denoted. The signs in the following tensor analysis depend on the convention used for the metric tensor. The convention used here is plus, corresponding to the Minkowski metric tensor. Electromagnetic tensor. The electromagnetic tensor is the combination of the electric and magnetic fields into a covariant antisymmetric tensor whose entries are B field quantities, and the result of raising its indices is where E is the electric field, B the magnetic field, and C the speed of light. 4 current. The 4 current is the contravariant 4 vector which combines electric current density J and electric charge density ρ. 4 potential. The electromagnetic 4 potential is a covariant 4 vector containing the electric potential phi and magnetic vector potential A, as follows. The gradient of the electromagnetic potential is given simply by electromagnetic stress energy tensor. The electromagnetic stress energy tensor can be interpreted as the flux density of the momentum 4 vector, and is a contravariant symmetric tensor which is the contribution of the electromagnetic field to the overall stress energy tensor, where epsilon 0 is the electric permittivity of vacuum, mu 0 is the magnetic permeability of vacuum. The Poynting vector is and the Maxwell stress tensor is given by the electromagnetic field tensor F constructs the electromagnetic stress energy tensor T by the equation, where eta is the Minkowski metric tensor. Notice that we use the fact that which is predicted by Maxwell's equations. Maxwell's equations in vacuum. In a vacuum, Maxwell's equations can be written as 2 tensor equations. The 2 inhomogeneous Maxwell's equations, Gauss's law and Ampere's law, combine into, while the homogeneous equations, Faraday's law of induction and Gauss's law for magnetism, combine to form, where F alpha beta is the electromagnetic tensor, J alpha is the 4 current, epsilon alpha beta gamma delta is the Levi eta symbol, and the indices behave according to the Einstein summation convention. The first tensor equation corresponds to 4 scalar equations, 1 for each value of beta. The second tensor equation actually corresponds to 43 equals 64 different scalar equations, but only 4 of these are independent. Using the antisymmetry of the electromagnetic field, one can either reduce to an identity or render redundant all the equations except for those with lambda, mu equals either 1, 2, 3 or 2, 3, 0 or 3, 0, 1 or 0, 1, 2. Using the antisymmetric tensor notation and common notation for the partial derivative, the second equation can also be written more compactly as In the absence of sources, Maxwell's equations reduce to, which is an electromagnetic wave equation in the field strength tensor. Maxwell's equations in the Lorentz gauge. The Lorentz gauge condition is a Lorentz invariant gauge condition. It is expressed in terms of the four potential as follows. In the Lorentz gauge, the microscopic Maxwell's equations can be written as Lorentz force. Charged particle electromagnetic fields affect the motion of electrically charged matter, due to the Lorentz force. In this way, M fields can be detected. In relativistic form, the Lorentz force uses the field strength tensor as follows. Expressed in terms of coordinate time t, it is, where p alpha is the form momentum, q is the charge, and x beta is the position. In the co-moving reference frame, this yields the force where u beta is the velocity, and tau is the particle's proper time, which is related to coordinate time by dt equals gamma d tau. Charge continuum. The density of force due to electromagnetism, whose spatial part is the Lorentz force, is given by and is related to the electromagnetic stress-energy tensor by conservation laws. Electric charge. The continuity equation expresses charge conservation. Electromagnetic energy momentum. Using the Maxwell equations, one can see that the electromagnetic stress-energy tensor satisfies the following differential equation, relating it to the electromagnetic tensor and the current for vector or which expresses the conservation of linear momentum and energy by electromagnetic interactions. Covariant objects in matter. Maxwell equation in matter. Free and bound for currents. In order to solve the equations of electromagnetism given here, it is necessary to add information about how to calculate the electric current, J. Frequently, it is convenient to separate the current into two parts, the free current and the bound current, which are modeled by different equations, where Maxwell's macroscopic equations have been used. In addition, the definitions of the electric displacement D and the magnetic intensity H, where M is the magnetization and P the electric polarization. Magnetization polarization tensor. The bound current is derived from the P and M fields which form an antisymmetric contravariant. Magnetization polarization tensor, which determines the bound current electric displacement tensor. If this is combined with F mu nu, we get the antisymmetric contravariant electromagnetic displacement tensor, which combines the D and H fields as follows. The three field tensors are related by, which is equivalent to the definitions of the D and H fields given above. Maxwell's equations in matter. The result is that Ampere's law and Gauss's law combine into one equation. The bound current and free current as defined above are automatically and separately conserved constitutive equations. Vacuum. In a vacuum, the constitutive relations between the field tensor and displacement tensor are. Antisymmetry reduces these 16 equations to just 6 independent equations, because it is usual to define F mu nu by the constitutive equations may, in a vacuum, be combined with Gauss-Ampere law to get the electromagnetic stress-energy tensor in terms of the displacement is, where delta alpha pi is the Kronecker delta. When the upper index is lowered with eta, it becomes symmetric and is part of the source of the gravitational field. Matter. Thus we have reduced the problem of modeling the current, J nu, to two easier problems, modeling the free current, J nu free, and modeling the magnetization and polarization. For example, in the simplest materials at low frequencies, one has where one is in the instantaneously co-moving inertial frame of the material. Sigma is its electrical conductivity, chi-e is its electric susceptibility, and chi-m is its magnetic susceptibility. The constitutive relations between the A and F tensors, proposed by Minkowski for linear materials, are, where u is the velocity of material, epsilon and mu are respectively the proper permittivity and permeability of the material, and denotes the Hodge dual. Lagrangian for classical electrodynamics. Vacuum. The Lagrangian density for classical electrodynamics is in the interaction term. The forecurrent should be understood as an abbreviation of many terms expressing the electric currents of other charged fields in terms of their variables. The forecurrent is not itself a fundamental field. The Euler-Lagrange equation for the electromagnetic Lagrangian density can be stated as follows. Noting, the expression inside the square bracket is the second term is therefore the electromagnetic field equations of motion, which is one of the Maxwell equations above. Matter separating the free currents from the bound currents. Another way to write the Lagrangian density is as follows. Using Euler-Lagrange equation, the equations of motion for can be derived.